Sorry, Zoom in. We had a bit of a delay here. I had some technical trouble.
Yeah, you couldn't get through the food line.
Yeah, I'm Kesta Schlippus. I'm just lurking as a guest, and I'm basically looking for a group for an astronomy club to join. I guess you're in Stockton. I live in Vacaville, and there doesn't seem to be anything around here.
Oh, that's too bad. Well, you're welcome to sit in with us. All of our events are open to the public, and there is a group in Sacramento. I think it's the Sacramento Valley SVAS. But yeah, you're welcome to hang out with us.
All right, good. Yeah, I guess I came across you and the SVASS, and I noticed that there a fellow named James Baldwin had all sorts of stuff, but nothing seems to be current online. Is he still active?
Oh yeah, he's at that's him coming towards the screen right now. Hey, Jeff.
Oh, okay, awesome.
That folder is not James folder. Is that where you're talking about? Yeah. Can you hear?
Yes, we can hear you.
Okay, did he say something about Baldwin?
Oh yeah, Kestis is checking us out, and he noticed that there were some discrepancies on some things that are out of date on your website.
Yeah,
Great, you're introducing me, knocking somebody I wanted to meet.
He can take it.
No, my website is not up to speed. It won't be up to speed until about March or April, but we do have to get rolling here. Is Becky back? Okay, we don't have to get rolling. There you go.
Yeah, we joke around a lot, so don't worry about that.
All right.
No, Jeff's a
Bruno guy. He runs on the wrong foot.
no, you're doing fine. Jeff runs our among other things our ATM group, the Amateur Telescope Makers. So he does some really cool stuff.
Yeah, excellent. In fact, that's what I wanted to do. I have a I made a mirror back when I was in high school, made a Dobsonian, and sort of fell out of the hobby completely. And I recently picked up a Meade telescope that I'd like to get an opinion on the mirror.
Oh, okay.
Okay, so we do have to cut this because we're already late. So my email is baldjb@comcast.net, and maybe we can continue this conversation elsewhere because we do have to get rolling here. I apologize.
Understood, Jeff.
Thank you.
So are we going from that one or this one?
You can share if you want. Or let me give you permission. You should be able to have these. I don't have your photos.
That's fine.
FYI, the picture seems to be moving in and out. I don't know what that's from, but we'll have to deal with it.
On the screen?
You can share.
No. I mean, like, is that the screen that's been flipping in and out?
Yeah.
Oh, okay. Working on selecting the correct screen. Okay. Yeah. I needed the Get this way so I can change. Is it changing at all?
Yes.
Okay, cool. That.
Are we ready?
Ready as I'm ever gonna be.
Okay.
But sorry about the delay.
Ladies and gentlemen, for those of you who don't have the privilege of knowing Rebecca, as I do, this is Rebecca Lewis-Merrill. She is working on her doctorate in astrophysics at UCLA. And she has been one of our members, our prize members, since 2012. She was one of our first Striking Sparks winners. I have the pleasure of remembering Rebecca when she was about 13, 14 years old, back in 2012. And I remember her asking me to sign her Striking Sparks sheet to prove that she'd been to one of our events. And I remember her when she was an extremely introverted, very shy young woman. She's changed for the better. Ladies and gentlemen, Rebecca Lewis-Merrill.
Am I supposed to be using the microphone or for the Zoom people, presumably?
We could use this one right here.
All right.
You don't want to hold it.
Yeah.
This should be close enough.
Can everyone hear me? If I get something to the back. All right. Just checking. Can people hear me on Zoom?
Can't hear her.
No? All right, get a thumbs up if you can hear me. Hello, hello? Anything? Better, okay. Does it come across clearly?
Jerry says better down there.
Okay. Hear better, but is it bad? Might need to pull up the chat too.
No.
Yeah, you could probably. Okay, testing 1, 2, 3. Okay. You might, Eric, if you go, you might be able to turn it up if you go to the settings.
It doesn't quite work that way the way I have it.
Oh, sorry. All right, well, I guess I'll just get started then. All right, as Doug said, my name is Rebecca Lewis-Merrill. I use she, her pronouns, and the pronouns game is a regular thing that is added on to things at UCLA because we also have non-binary pals at UCLA and around the world. There are more. I'm married to a non-binary person, so visibility is important for the LGBTQ community. So, all right. So I have been a member since 2012 when I was an 8th grader, and I eventually became the newsletter editor about November of 2014, and succeeding Trevor, and I succeeded Trevor Atkinson in the board election in 2015. And currently I am a 2nd-year graduate student at the University of California, Los Angeles. I studied the galactic center of our Milky Way galaxy. My advisor is Dr. Swan Doe in the UCLA Galactic Center Group. However, the private investigator of that lab is Andrea Getz, who you might know as the woman who won the Nobel Prize in Physics in 2020. It's a very exciting thing to be doing. However, that is not what I'm talking to you about tonight. Tonight, I'm going to be talking about the largest moon of Saturn called Titan and its hydroclimate of liquid methane. Now, Jerry told me that y'all might appreciate some context for this whole tale that I'm about to tell you about my research in the paper that just got published a few months ago on my work. So I'm just going to spend a few minutes doing that. And so that I stay on time, Jeff, I'm going to start a timer so that I know I am not overdoing it. All right, so it begins. So after y'all got me all addicted to space and stuff, I entered the world as an astrophysics major. And I must say that y'all got me addicted to space and then unleashed me onto the world. I do not do anything by halves. So everything you're about to see is your fault. So this picture is from my freshman orientation. I'm right there in the screen. This is a fountain in the tradition for freshmen at UCLA is that we dip our hands into the water in the court of sciences and we swear the true Bruin oath or something. I do not remember what was in that oath. What I do remember is that my student tour guide told me that if I touched the water again before I graduated, that I would be doomed to another quarter at UCLA. A quarter is another 10 weeks of classes. The fact that the fountain broke before I graduated should have been an omen because I'm still there. I went to the same place for graduate school that I went for undergrad. So what does one do as in their first couple of years at a supposedly world-class research institution, yada, yada, physics. That's what you do as an astronomer. So the usual suspects such as demos like standing waves or Van de Graaff generators, and it makes long-haired folk like me have really staticky hair, lots and lots of math, and a lot more programming than I thought I was getting into. My whole job these days is programming. Literally, that's pretty much what I do. However, there was a particular highlight. I joined a space-oriented engineering club called Bruin Space. I became the project manager of their science payload division, and another division of the club launched our muon detector into the atmosphere on a weather balloon. Now, picture this. The math science building at UCLA is rooms upon rooms added together, not really with much rhyme or reason, and it's on a hill. So no one floor has the same layout as the one below it. Some floors aren't even connected across the entire building. And then you've got this little shed on the top of one of the roofs. There's multiple roofs, by the way. And it was originally set aside for seismic detectors. Well, the engineering department told Bruin Space, oh, you can convert this into some lab space, just don't touch the seismic detectors. So of course there was red tape all over that. But so they brought in computers and oscilloscopes on top of workbenches that looked like they had seen much better days. And we had chairs from both the STEM buildings and definitely ones that they stole from humanities, because I recognized that chair from one of my other classrooms. And a couch in the corner that looks like it's about to die if someone sits on it. And computers and microcontrollers and radio equipment everywhere. That's the room I learned to solder in. That's the room I learned the program in. It's also the room I learned how to walk away from a project that isn't working. I did not have enough time in my schedule to be devoting to an engineering group that wasn't working. So that's what I learned, an important lesson on, even if you're not done with something, you can walk away. There's no shame in taking. That was one of many lessons on taking care of yourself and not just dying for grades. So I ended up working the summers while I was at UCLA additionally. The first summer I worked at a book shop. That was one experience. I'm not really going to elaborate on it because retail and that was definitely something I didn't want to repeat. So what does one do in that case for the next summer? Find a job that's related to your major. So I became a teacher's assistant for an introduction to astronomy class for middle schoolers in the Johns Hopkins Center for Talented Youth. I spent the summer designing labs and activities for my students. And I also convinced the management to let me keep the kids out after dark so that I could give them tours of night sky using telescopes I found in storage that had been forgotten for 5 years. I took inventory. That was a lot of inventory. So I put some of the scopes together, figured out what worked, and got to give my students some tours of the night sky. We also finished up the summer with a field trip to Mount Hamilton. And on the left is the group I was teaching, and on the right is the Shane 3-meter telescope. That is not the last time I would see the Shane telescope. More on that later. And so around this time, about the fall of that year, I was writing an article for the Valley Skies, actually, and I wanted to do it on the climates of other terrestrial worlds in the solar system, moons included. What I found was a review paper of a bunch of basically a review of other papers, called The Climate of Titan, that was written by Dr. Jonathan Mitchell and Dr. Juan Lora. Well, it turns out that Dr. Jonathan Mitchell is at UCLA. And on a whim, I decided to get a geophysics and planetary physics minor so that I could eventually take a class with this man. Several months later, I finally finished. I was midway through the class, finally got up the courage to ask if I could talk to him about his paper. And we spent about 2 hours in his office talking about said paper. And at the end, he offered me a position as an undergrad researcher, which is how I got my first undergrad research experience. So far picture upper left is me presenting some preliminary results from that project, which are actually going to be in part of this presentation at the Conference for Undergraduate Women in Physics. Later that year, I presented at a bigger conference called the American Geophysical Union Fall Meeting. That was in San Francisco at the Moscone Center. I tried to include a picture, but picture a poster hall as big as a football field, with everything from tectonics and planetary interiors to exoplanets. Go from the interior of the planet out until you get to the edge of the solar system. Then the planetary people don't consider it their problem anymore. This is the lab group. This is down here. The blonde guy is Dr. Jonathan Mitchell himself. And so I did that research. However, I wanted to try out something more astrophysics related. So I got a summer position with the Galactic Center group. It goes way back. So, and this is an outing where we took to Andrea and one of the other PIs took us to go see Sophia while it was grounded. So we got to have a tour of the telescope and the facility, and that was tons of fun. So a couple years go by, and I'm still working with the Galactic Center group. I have now graduated undergrad. I have done a post-baccalaureate research position with them in my gap year between undergrad and grad school. And I entered grad school and I'm still working with them. I must say, Dr. Twando is a great person to work with. He has an amazing mentoring style, and that's most of the reason why I kept working with the Galactic Center group. Unfortunately, I forgot to put a picture of him in. But if there's work, there is on the far right, I have a picture of some observations that we're taking of the Galactic Center from the Keck telescope. Because our group uses, you want to just look at it?
Zoom in, I can still hear you.
Okay, so we were, sorry. So the GCG uses the NERC2 instrument on the Keck telescope on Mauna Kea and Kauai. So we have to remotely operate the telescope. We have a remote observing room at UCLA, and we take observations from afar using that. Infrared wavelengths are the only way you can see into the galactic center with all the dust and gas in the way, as I'm sure everyone here is familiar with. Additionally, I managed to get into an observing workshop for early graduate students called the Lick Observing Workshop. And me and other grad students from the UC system got to go up to Mount Hamilton at the Lick Observatory and operate the telescopes for a weekend. So we planned out an observing run, which is me and all the other people staring at our telescopes over there. And then we actually operated the Shane telescope. And the one thing I learned that weekend that sticks in my mind is, one, telescopes are very heavy machinery when they get that big and they can't crush you. And two, don't point the telescope at the ground because that can and will happen. So my current research that I'm doing now, not the Titan stuff, but I will get to that in just a minute. I got to present my Galactic Center research at the American Astronomical Society poster, first one I ever attended. People might not be familiar with that, but that is the conference for astronomers in my field. And also, the most interesting thing that happened very recently was that all the UC grad students went on strike.
Oh.
I mean, we make an average of 24K in having to live in LA and set 60 to 70% of our paychecks are going to rent across California. So yeah, we needed more money. So we went on strike. That lasted a month. So that is me wearing my Galactic Center group hat because I must represent my group. And that is us marching down Wilshire Boulevard in Los Angeles. All right, so to the actual event of the night. I hope that was informative on how we got to me being here talking to you, you watching me talking. All right, so Titan, largest moon of Saturn. It's about 180% the mass of our moon, and it has a radius 1.5 times of our moon. However, its gravity is lower than our moon. It's about 85% of our moon because it is bigger in radius, even though it has more mass. So you might notice it just looks orange. That is a haze of Thorin molecules at the top of its atmosphere. However, and this is in optical wavelengths. However, if you start looking in infrared, things start getting a lot more interesting. So these are 3 different views taken by the Cassini spacecraft at different points when it was flying by Titan. On Titan, you can start seeing these dark zones around the equator, and it starts getting lighter toward the pole. Those dark areas are actually deserts of organic particles. What exactly the sand particles are is still up for debate, actually. It's still under investigation, but we know it's sand and there's dunes and it's a desert. So let's start at the top, quite literally. So this is a column diagram of Titan's atmosphere. Up here, about 900 kilometers up, this little dot, sorry, it's probably not very visible to people in the back, is Cassini's closest approach to Titan. You go about another 400 kilometers down and you start getting to the haze layers that are what you mainly see when you look at Titan. And then it gets thicker as you go down through the stratosphere, and then down the stratosphere, the last, like, from the surface, that's where you actually start getting the liquid methane level, which is the stuff I'm interested in. So important to know about Titan is that it rotates very slowly, actually. Its surface rotates slower than its atmosphere. The atmosphere rotates 200 meters per second, or about 500 miles per hour, faster than the surface. So Coriolis forces on the atmosphere are much weaker than they are on Earth. On Earth, you have Hadley cells that dump water in the tropics around 30 degrees. latitude. On Titan, the half cell goes all the way to the poles. This means that moisture in the form of liquid methane goes all the way to the pole rather than having tropics. What this results in is wet poles in a desert belt at the equator. So I realized I didn't talk about it much, but remember that Titan is very, very cold. It is about negative 300 degrees Fahrenheit. So water is very frozen. And water ice, when it's frozen, is a mineral, like a rock. On Earth, we have silicates and basalt and various olivine, and my spouse could tell me many, many more. They're the geophysicists, not me. But water ice on Titan serves a similar function to rock on Titan. And it is so cold that that methane, which is a gas on Earth, condensates into liquid. So you have methane and ethane clouds, rain, channels, rivers, lakes, seas. This is a map of essentially the geomorphology of Titan. Up toward the northern pole, you have many, many lakes of liquid methane and ethane. The purple is the organic compound deserts that we see. And we have images of sand dunes on Titan from those regions. It's called shaped a lot. The orange regions are what is called hummocky terrain, which is, think hilly terrain, hilly and somewhat mountainous terrain. The labyrinthian areas, especially at the South Pole, are much more tectonically jagged. So if you think of uplift and mountains that are made by tectonic plates coming together, that's the sort of thing you're seeing there. And green, which is most of the surface, is plains. There might be a lot more interesting features in these plains. However, with the resolution that we did manage to get from Cassini, we only have a couple of data points. One of them is from the Huygens probe that landed on Titan. So that brings me to fluvial features on Titan. You have a definitely active hydroclimate. We have seen rain and we see the lakes. So these are images from the Huygens. Sorry, I just looked up how to pronounce it. I'm just going to call it Huygens. As it's coming down, and you have these dendritic type features that you see with fluvial erosion. They're a little hard to see on here, but you can also see some of the scalping on, these are flat projected, so it's distorted, but you can see sort of where you might get fluvial erosions down the mountains. Additionally, we've got the lakes here, which cover, total area of these lakes is 620,000 square miles, or about 4 Californias. Lewis-Merrill up here, which is one of the smaller big ones here, has the area of Alabama. So these are bigger than the Great Lakes. So they are basically seas. They're sometimes called lakes, sometimes called seas, depending on whether you're comparing it to inland seas like the Black Sea, or whether you're comparing it to the Great Lakes in the United States. All we know is that they're composed of methane and ethane, mostly methane in the northern pole. There's like one lake in the southern pole that's more ethane based. And the reason why you have more lakes in the northern pole is because the current configuration of Titan's orbit means that more liquid gets dumped on the north. All right, so there's a lot of fluvial features. The one I was primarily interested in my research are called alluvial fans. So if you picture rain on mountains, you will have runoff over the slopes as it goes downhill. That runoff will pick up sediment and I can't say soil because it's not going to be soil here. We'll pick up rocks, debris, and stuff as it flows downhill. It will eventually collect in some sort of river or stream. and it will continue going downhill. On the sides, you will get, it will be encased on both sides by the sides of the channel that it's running down. However, once this hits a lowland, you lose confinement on the sides, so it spreads out. And because it spreads out and the slope has now changed, the flow of the stream slows down and the sediment gets deposited because it's no longer able to be carried by the fast running flow that you had before. And you get these alluvial fans that can get deposited. Now, we had in 2016, Samuel Birch and his team looked through all of the radar data that we have of Titan. In total, we have about 61% of Titan mapped in radar. We don't even have the whole thing. So, and these are also fans that are big enough to be at least 10 square kilometers, which I don't know what it is in square miles, but they have to be big and to be able to see seen in the resolution of the images that we have. But in total, Birch and his group found 81 large alluvial fans across Titan. Now, and these are images of some of the alluvial fans. You can see that we suffer a bit from a resolution problem with the radar that we have. So to tell you what's going on in these pictures, where it's dark means that the ground is more smooth. Where it's bright, that means it's more rough. Because the way that radar images work is that you send the radar down and it bounces back. If you get more scatter on it, it shows up brighter. If it's smooth, then it shows up darker on here. So you'll see on some of the, where the fan originates, it's brighter than some of the surrounding area. This image isn't, this D isn't from Titan. It's from Birch's paper, but this is essentially a comparison of these images to what you might see in Death Valley. So this is from Death Valley, the others are from Titan. Okay, so we have alluvial fans on Earth. That's how we primarily study them. So there's a couple images here, one from Death Valley and another one from Western China. And you can see the feeder channel for the alluvial fan for where it spreads out. Death Valley obviously doesn't get much rain, but when it does, it rains hard. And because the ground is so dry, it does not infiltrate into the surface. So it will just run along and carry sediment with it, which is how you end up with actually a larger density of alluvial fans in Death Valley than in some other areas. You can also get it in regions that have consistent flow of water or liquid. As you can see, the sort of river going down the one from China. We also see alluvial fans on Mars, which definitely does not have an active hydroclimate. So this is one image of an alluvial fan in a crater on Mars. And this is a map of all the alluvial fans that the red ones are alluvial fans that we have found on Mars. The background map to this is actually a topographic map of Mars, where it's the northern pole is lower than the southern on Mars. So the ocean, when there was water, would have been here, I believe, unless I got that backwards. All right, so Earth has an active hydroclimate and has alluvial fans. Mars definitely does not have an active hydroclimate, but it does have alluvial fans. So we can use those alluvial fans as markers of what the climate used to be on Mars. So the question I pose is, are the alluvial fans that we see on Titan the result of the present day climatic conditions, or are they result of ancient environmental conditions on Titan? There is 1 year that goes by on Titan every 30 hours. We have only half a year, only half a Titan year of data on its seasonal change. We don't even have a full turn of all the seasons on Titan of data. So if I want to test whether or not these alluvial fans are a result of present day conditions, let's assume that, okay? Let's make the assumption that alluvial fans are a result of present day conditions. How do we test that? Well, it starts with two different assumptions. The first is that where you have that the spatial distribution of your alluvial fans, this is fake data, bear with me, where the spatial distribution across the map, where you have, the spatial distribution of those environmental factors is going to be related somehow to the observed alluvial fan distribution. So let's say that you need more than 100 millimeters per day of rain to get alluvial fans for the type of geologic conditions that you have. If you need that much, then you're going to only expect to see alluvial fans in those locations. The second assumption is that these alluvial fans are actually created by these environmental factors. I break this up into two different assumptions for the following reason. The environmental conditions that create alluvial fans mainly include having the right enough sediment to deposit and make the fan, and enough flow of liquid to carry that sediment. If the storm occurred a long ways away from where the alluvial fan ended up, because it was a long slope downward, then you're going to have the environmental conditions in a different place than the alluvial fans. However, we don't have enough data to be able to test the idea of our alluvial fans from present day conditions if they're too far away from each other. We just don't have the data right now. So I have to make this assumption that where the conditions occur is where the alluvial fans occur. It can't be indirect, at least for the investigation that I did. So if these assumptions are correct, we should be able to take some subset of these alluvial fans, make a model of what environmental factors correspond to the alluvial fans. And then using the model that we made, we should be able to predict where the rest of them are. Does that sound reasonable? Any questions so far? Any clarification questions? Yes.
Want me to ask questions, or do you want me to wait till you're all wrapped up?
Wrapped up, okay. All right, so here's the workflow of the investigation. I take my data, I split it into, most of the data goes into what's called a training set, most of it goes into the testing set. This is the set we're going to try to predict later. We make our model. We have the model calculate the likelihood of alluvial fans on the map, and then we test to see if our alluvial fans are in those high likelihood zones. So the data that was used falls into two categories. The first is climatic data, which is precipitation, and the second is topographic data, which includes slope and elevation. So I already told you that we only have half a Titan year of precipitation data, essentially. What we did in order to make sure that we had predictions of the rainfall in all the areas, we made a 3D atmospheric model called the Titan atmospheric model. We made it self-consistent such that precipitation would fall, infiltrate into the subsurface like the water table on Earth, evaporate, and then go back into the cycle. So we made a fully self-consistent 3D atmospheric model to test this. And it takes like a month to run each time you press the on button. And we benchmarked it against Cassini observations. And it replicates the observations that we do have from Cassini for that half Titan year. Additionally, I mentioned earlier that we only have an incomplete map of the surface of Titan. So for topography, we took what topography that we do have, and another group interpolated what the rest of the topography should be given the gravity parameters and other measurements that we get of Titan and what we know about it. So now we have topography and climate. So the 6 factors I test, so this model can run in 2 modes. I can predict where alluvial fans are based on one environmental condition at a time. be that precipitation, elevation, whatnot, or I can take all the factors together and predict the likelihood. So this plot shows for the probability models that I mentioned earlier, I train it using each of these individually. And this score at the bottom is how well it correctly predicts the high likelihood zones of alluvial fan occurrence. So if it does well, that means that it predicted high likelihood of alluvial fans in an area where there actually is alluvial fans. The numbers correspond to the probability that the model ranked a zone with that actually has alluvial fans is higher than one that doesn't. So this is probability of it got it right. So you can see that slope and relief, which is essentially the elevation between the fan and the highest, well, the local highest mountain where you would expect the runoff to come from, only did about as well as if you did it by random chance. So those factors did not do well. However, some of the ones within their error bars got about 65 to 70% correct, which if you compare this to other papers that use the same methods we did, is actually pretty decent. The type of probabilistic model that I used is also used for mapping landslide susceptibility in a lot of areas. And when you put all the factors together, we got about 73% correctness on that. So given that all the factors together do a pretty decent job at predicting where the alluvial fans are, this is a map of the likelihood that came out of that model. What these numbers mean, one is it predicts likelihood equal to the average. So if you took, what's the probability that if I go somewhere, I'm going to find an alluvial fan? That's average. So blue is higher than average likelihood of finding a fan. Red is lower than average. So blue regions, we expect there to be alluvial fans, and red zones, we expect there to not be many in terms of density. So there's a lot gathered around the upper latitudes in both the northern and southern hemispheres. And then we have a sprinkling of them in the equatorial regions. The hatchings on here are regions where we didn't have any surface data observations, so we extrapolated to those zones just to predict whether or not there might be alluvial fans there. And these blue regions correspond to areas with high amounts of precipitation, areas that have low variability in precipitation, meaning that you usually have the same magnitude of storms coming through, and areas with low elevation. So there is definitely a strong latitude dependence that comes from the precipitation, but you'll notice that there's also some lighter blue regions throughout that correspond with the lower elevation areas. So, my key takeaways that I would hope you remember tonight. Titan has a methane hydrological cycle. And we can use geomorphological features on a terrestrial world like Mars or Earth or Titan to determine what the climate might be and to learn about past or present climate depending on what's currently affecting the surface. And additionally, because the present day conditions on Titan corresponded to the areas where we have more alluvial fans, we concluded that yes, these alluvial fans are being created by present day environmental conditions on Titan. So that means that the geomorphic fluvial erosion is ongoing on Titan. Titan is a living, well, for a planet, it's a evolving environment. It's not dead like Mars on its surface or as dead. It takes a long time for a year to go by, but there is ongoing erosion going on Titan. And that is all. Sorry if I talked a little fast. Questions?
On Earth, you have sodium chloride all in the ground and built on the river, you know, salinating.
Yeah.
Is there a salt on Titan that you're aware of that's causing the same thing on these lakes?
We do not know. We have more knowledge of the geomorphology on Titan than we do the actual geology. Because the measurements that we have from Titan are mostly radar and infrared observations. We don't actually have any composition measurements from the surface. We can use the penetration of the radar to, we determined that it was methane and ethane in the lakes. However, the particular traces or the salination levels, we were not able to determine as far as I'm aware. Doug?
So we know that water ice basically is acting as rock.
Yes.
What, do we know of the other forms of liquids or whatever that turn into solid rock because the both
Well,
be there? I mean, what other things besides ice, water, and you solid?
there would be other ones as well. Most things that would be liquid at room temperature here on Earth would probably be rock there.
What is on Titan that is shown to be the rock, so to speak? Other than
I don't know off the top. I unfortunately do not know off the top of my head. I do recall there is a lot of sediment on Titan that is made of hydrocarbons and organic molecules, which organic molecules are ones that include carbon. And a lot of it's how they exactly got there, we're not quite sure because they're smaller than the aerosol particles in the haze on Titan. So there's multiple processes under debate for how did the granules that create the sand seas on Titan get.
was the harshness of these different things. So that you
Yeah.
know what the alluvial fans are mostly made of, like granite or talc or whatever.
Yep,
here on
yep.
Earth.
Um,
Each one's gonna react differently to different harshness.
as far as the research that I did, yeah, as far as the research I did for this project, mostly organic molecules. Because the assumption is that it's mostly going to be like the sediment that the granules that are in the sand seas
Right.
lower down.
Sands were consisting of.
No, it's we are very much we are pretty in the dark on that because we don't have any direct compositional measurements except from whatever we were able to get from Huygens. And that was just one data point on Titan's surface.
So the next one.
Yes, the one that you should watch out for is Dragonfly, which is coming in the 2030s, which is going to be sort of a flyer / lander on Titan. It'll be using its atmosphere to fly over distances and cover more ground. Yes.
You mentioned radar.
Yes.
studies. Are they ongoing studies and how, and from what points are they studying?
For the most part, the radar data that I mentioned was from Cassini, and Cassini is now somewhere in Site Center.
Okay, so in other words, there are no current, you're not doing.
Not currently, to my understanding. There are some infrared things going on for research on Titan. There have even most recently where JWST looked at Titan and saw several clouds around the northern pole. That should be Google. Oh, also, I just remembered. For Doug, for your question on the sediment, there is a study I could send you the paper for that it looks into what the material might be based on the amount of erosion seen in different points. So I could send you that.
The hardness level with the various
Yeah.
things. That's gonna be your early.
Yeah. I'd need to take another look at that paper. It's been like at least a year. Yes.
I have a question from Lara Grimes, on Zoom right now.
Okay.
Were you on one of the Sophia flights?
No, I was not. I just got a tour of the
You might
telescope.
repeat the question, the microphone in case you can't hear me.
What?
Say the microphone.
The question was, did I ever go on one of the flights on Sophia? And the answer is no, I was only able to go on a tour of the facility because one of the professors in my current lab group was one of the mission directors of Sophia. Eric something. I cannot remember his last name for the life of me right now. Any other questions? Jeff?
The moon and Earth have billions of year old surfaces, and Earth has hundreds of millions of years old surface.
Mhm.
Any idea the ancientness of Titan surface?
Okay, so the question was for the people on Zoom that there are ancient surfaces on Mercury, on our moon, on Earth. How old is the surface of Titan? So that question I actually can answer a bit. So the plains, the map I showed earlier, this one. So most of Titan is covered geomorphologically by plains. It's like flat, generally brown. There are channels in these plains, but for the most part, it's somewhat sloped land. But the thing that you should notice on here is that we have a couple of craters, not many. Usually you see craters on older surfaces such as the moon and Mercury, but you'll notice a lot less craters, say on the Earth, where there is ongoing erosion and movement of surface sediments by the weather. Titan has a similar thing going on. So I can't speak to like the age of continental crust on Titan, but I can say that it does have some sort of recent continuous resurfacing due to erosion by wind and liquid methane. Which would probably be more around the millions of years than the billions of years. Yes.
You're also saying that Titan rotates a lot faster than the atmosphere does?
No, Titan's surface rotates slower than its atmosphere.
Yeah, so quite-
It's more or less, it's pretty tightly locked.
Which basically sets up wind
Yes,
and I'm assuming those wind speeds are somewhere at the equator different than at the poles and.
yeah,
What's the-
on average, the winds relative to the surface, like they're about 450 miles per hour,
okay,
compared to the surface.
there's your flatness right
These measurements, I must say, are higher up in the atmosphere,
there. Still,
so, it probably doesn't propagate all the way down to the ground.
gonna have
Yes.
the winds.
Yes, and that is what in the deserts on Titan, this results in longitudinal dunes
Right.
that are just like stripes going along the longitudinal lines as the wind goes by.
Time we get there, all the winds are-
Yep, they're different every time we look at them. Yes,
I'm curious, what is the pressure, let's say atmospheric pressure at the surface?
the atmospheric pressure at the surface of Titan is about 1 atmosphere of Earth.
So there's those winds, 450 mile-an-hour wind. Quite a bit of work on this.
Yes, they do.
Would that end up causing the alluvial fans to be covered up or
Potentially, a lot of the smaller ones have been covered up by just wind sediment being deposited on them. The data set that I was using are, these fans are the size of mega fans on Earth. So that is one note of the study that I was doing is the alluvial fans that I was looking at are the giant ones that didn't get covered by wind sediment or eroded away by yet another liquid methane river. Yeah, so wind definitely plays a big part on the surface of Titan. And additionally to the atmospheric pressure question, it is important to note that the hydroclimate of Titan differs from that of Earth, that Earth, most of its liquid is in its oceans. On Titan, most of its liquid is in its atmosphere. So the reservoir is in a different location. Which doesn't quite relate to your question, but I thought was a cool fact, which I'm sorry. Tim, since you haven't.
Rebecca, the family and I are planning a trip to Titan soon. And are the seasons on Titan? When should we go?
Do you want rainy or sunny weather?
Sunny weather.
Well,
Sunny
just
weather?
break this
Okay,
rainy weather.
well, if you're looking for sunny weather, just in general, I'd say go to the desert.
Okay.
Bring warm protective gear and some oxygen. You shouldn't have to worry about the pressure.
Are there seasons, like there are on Earth?
Yes, so generally, it's more of like a California winter rather than like a Midwest winter. You get rain when it's winter. And you mostly get the rain at the pole. So when it's winter in the northern hemisphere, you get more rain there. The southern hemisphere does get less rain during its winter, just because of the current orbital configuration of Titan around Saturn. That orbital configuration gives it changes in its tilt, like Milankovitch cycles on Earth.
Did you mention how long a year was?
30 Earth years. Because since it takes about 15 days to go around Saturn, which is equal to a Titan day, because it's like tidally locked with Saturn. But a Saturnian year is essentially a Titan, which is 30 Earth years. Yep.
Since it's tidally locked, is the core being stressed and heated, and can that affect the weather?
Yes. Most of the energy in the atmosphere on Titan that is currently there comes from tidal effects from Saturn rather than being solar powered. Especially because of the haze layer at the top of Titan's atmosphere, it doesn't get much to the lower levels of its atmosphere.
Is there any point in this atmosphere that is cold enough to have solid crystallized methanol
Methanol,
or methane, any crystallized methane? I-
crystal methane, like ice, methane ice.
Has ideals.
Okay. I am not sure. I spent more time on the interaction between the atmosphere and the surface than on the atmosphere itself. However, I would not be surprised because we do have, I think they're called cirrus clouds on Earth that are like water ice. Let's see. Yeah, we have we have methane cirrus clouds about 20 to 30 kilometers up.
Oh, yeah.
Yep. Yes.
Yeah, Rebecca, I was just wondering, with all those complex, with all of those organic compounds floating around, are there any relatively complex hydrocarbons, maybe basic amino acids or anything that might just show that life could maybe develop?
Well, so I want to back up a little on that question to answer it. The way that it's thought that organic compounds were able to organize into organisms on Earth is because a lot of the organic molecules were suspended in water. And that allows them to float around and connect together and do lots of funky stuff. And eventually through trial and error, it's thought that you get life. If you go just straight with the evolution model, which is what I believe in. But on Titan, so the particular quality of water that lets it do that is it being a polar molecule. It can attract, it can make more complex structures than itself by adding water to different molecules. Methane, on the other hand, is not polar like that. So it is much less likely to create different structures and molecules and stuff in a way that would make life as we know it.
Polar meaning magnetic?
Yes, like positive and negative
Sure.
sides of a magnet,
Are
yes.
there any hydroxyl components in it that where it could happen? No, like methanol, but speaking of methanol, you have a hydroxyl, oxygen and hydrogen, which makes it polar.
I don't believe so. To my understanding, I don't believe so, but
Mike, I said methanol when I meant methane.
No, I helped you to the first.
okay, other questions? Yes,
Physics question and political chemistry question.
okay,
I heard you say something that was kind of curious to me. You said that the hydroscopic or not hydro, fluidic ocean
Yeah.
on
yeah, the,
is actually in the atmosphere above the planet.
oh, yes, so most of the reservoir of methane on Titan is primary, oh, the fluid.
Fluid.
Oh,
Not
so,
necessarily the methane, fluid, is the equivalent of our ocean here.
what, sorry. Yeah, so we have liquid, so on Earth, I might have not said that correctly. So on Earth, we have a water cycle, and most of the water on our planet is, most of the water molecules on our planet are in the ocean. So our reservoir of water is mostly our ocean, with some water vapor in the atmosphere. On Titan, you have more methane vapor in the atmosphere than liquid methane on its surface. So for the entire hydroclimate, the whole cycle of it, you have more atmospheric methane than you do have liquid methane before it like forms clouds and then rains.
The real question at hand.
Okay,
What we're looking at, the radar reflections. That would be equivalent of ground penetrating radar, so that we can look at cloud, Mariana Trench, so to speak. Or
I believe so. Depending on the images I showed before, I don't think are the penetrating radar, but we have measured the bathymetry of the lakes using radar. Yes, and they're a couple kilometers. They are deep.
So it's like there's an ocean on top of an ocean. Ocean of
Well,
lighter fluids of.
No. The methane in the atmosphere is gas. But like there's water vapor in the atmosphere on Earth. So think of ocean and then atmosphere like on Earth, except it's more saturated in the atmosphere. Sorry.
Now, your first image showed it pretty well.
Okay.
The cloud layer on the top.
This one,
No,
this one,
or even earlier in, I think that one there,
that's a haze layer.
that haze layer, is that methane?
No, that is actually photolyzed methane made into thorium molecules. It is if you take methane molecules and then you hit it with photons, it breaks apart into this organic haze. So the methane reservoir in Titan's atmosphere is actually being continually assaulted by the sun. Any other questions? We have maybe time for a quick one. No, I'm getting thrown off the stage. Okay. Any other questions? If not, then I believe that concludes our presentation. Ta-da!
Okay, thank you, Rebecca. Well, my wife and I've had the privilege of hosting you for this visit here, and I realized just how little I know about anything talking to her. It's been quite interesting. Well, I know crystal meth is on Titan. That's all I know. Okay. All right. Is it on? Yeah. All right. So at this point, I think we need to make our installation part of the evening here. And what I'd like to do is have our new members come up front. We'll introduce them. I don't have a gavel, unfortunately. We can thank Jerry for that, who's not here. But anyway, so, Jerry, why did not you give me the gavel? Yeah, thank you.
The gavel was in the box I gave you yesterday.
Then, yeah, I gave you the box. Well, it doesn't matter. We'll find it. Don't worry about it, Sherry. It'll show up somewhere.
I'm not gonna lose any sleep.
Okay, please, all of you, including Rebecca. Okay, so I will stand this way, facing. Okay, and then we have Jerry in the background. And John couldn't make it, I guess. So this will be an abbreviated one here, but as president, what's that?
We have
New members is what we want. Bill, why are you hiding? Come up there. You have to listen. Part of being in this elite club is listening. Okay. Put you over there because we're doing this a hierarchy of importance, starting with me. Yeah. Okay. As our newly. We have.
You guys scoot together so we can get a picture.
Okay, so we have Tim Clark as our new president. As vice president, Doug Christensen, who's been a staple in just about everything here. Treasurer in the background is Jerry Hyatt. Secretary, Eric Holland, and he's been exceptional as well. Our newsletter editor is the notorious Rebecca Lewis-Merrill. Thank you, dear. Bill Lytell is one of the members at large. John Schimpf could not make it. And I guess Nehart is not here today, is he? So anyway, we'll do him in abstention. So this is our newly elected executive board members here. And I'd like to have you give them a hand, please. And so I will pass on the gavel.
There's your gavel.
I'm retired.
I got
Congratulations.
Thank you, Mike. So, I guess I take over now. Yeah. So you guys are all, helping me coach me along here as I get used to the new role. I do have a couple of awards, but before I get into those, I want to thank our host, Penny. Thank you very much. As she mentioned earlier, we have a long relationship and we've got a lot of great opportunities in this association that we're building with San Joaquin County Office of Ed. So I want to thank them. I want to thank all the members present and online that have made this society just the great place it is to come for whatever reason you come. Some of us come for the technology, some for the social aspect, all kinds of different reasons, but it's a really fulfilling experience I found. And so that's why I'm really looking forward to serving as president and making it an even better society than what has been handed us so far. So Jerry does a great job as treasurer. He guides us along. I think Jerry has been every position in the club. And so if there's something you need to know, Jerry's there for us to guide us along. Eric is kind of the unsung hero of the whole crowd here, is that he didn't eat tonight. So everybody, give him some sympathy because he's the one that didn't eat. But and I'm sure he had a couple of nervous breakdowns and his high blood pressure shot through the roof when he couldn't get the IT stuff working. But Eric, thank you very much. You do a great job every time. Yeah. Not here with us tonight is a new member, a member at large, John Schimpf. He was sick, so couldn't make it. He and Bill Lytell are our new members at large. So we're going to put them to work doing all the heavy lifting because they're the new guys, right? Let's see, who else have I missed? Doug, I had to make a deal with the devil to get him to take the position as vice president. So more details on that as we go through the year, but we're all working together to bring monthly programs, events, and activities to the club. So that's our goal. Really look forward to this next year. Okay, so I do have a couple of awards in recognition for somebody, the two gentlemen that are outgoing from the board that have done just so much. And so Jeff, if you'll come forward, Jeff is the guy that he likes to give this kind of this wacky award once in a while to different members. He calls it the 1% award. And anybody here received a 1% award? A few of you've got it. Yeah. Yeah. So I don't know where Jeff came up with that. So we had to one up him on the 1% award. So Jeff, if you'll open the, unveil this and read the inscription on that plaque. Yeah. 1% is from 1% of the population sees mercury. Right. Really nice spray. Less than 1% award. Less than 1% of the population will orbit the moon to observe the an Earthrise. Less than 1% of the members of the Stockton Astronomical Society will ever contribute as much as Jeff Baldwin. Jeff has done everything and he continues to do so much in the club. Thank you, Jeff. You're leaving, but you're not stopping all your activities. No, this is mine. So we come to Dr. Mike Lavieri. Mike, you've been president for 3 years now, I believe. 3, 4. It just seems like more, right? So Mike retired from his practice just a year or so ago. And at about the same time, he started twisting my arm really hard because he wanted to really retire from work, from his practice, and from all the things that kept him busy with the club. So Mike's done so much work to keep the club going, restored our finances, got us on track in so many different ways, and it's kind of made the great group that you see here tonight. So Mike, we have total appreciation and really, really thank you for that. So in appreciation, Doug and I and Jerry put together this display here. And so I'm taking the tablecloth home. You already have one? Oh, wait, let me take it back. So, yeah. So, Mike, in appreciation for all you've done from the club, please unveil your outgoing president's award here, please.
I expect to see a leg kicking me out.
Yeah.
Oh, wow, that's right.
Yep.
And thank you very much.
Yeah. So,
In my office.
there's a little description there. It says in appreciation, but for those of you that don't know, you all help me out here, but our founding member was Dr. Clarence Custer in Stockton back in the 1950s. In fact, the club was founded in 1950. In just a couple of years, we're going to have a 75th anniversary. So he was kind of the cutting edge of technology, telescope making, and astrophotography back in that day. He took this photograph using his homemade telescope in his backyard from Stockton on glass plates, if you will. Transferred those glass plates then to photographic film. And then these, there were copies of the original that were still at UOP. that Jerry has generously stored for us at UOP. So anything to add on this photograph is really kind of historic and meaningful to the club.
Say something. I believe I'm an oldest member of Stockton Astronomical Society, 1971, when I got out of optometry school.
The longest, oldest
I
member.
joined the SAS, and everyone was old, like me. It's not for me. Lasted 1 year, and I did not go back until Jeff recruited me about 30 years later. Okay, so he got me beat. And the other one is the telescope that he photographed this through. I actually had an opportunity to look through it, and it was quite ingenious. It's called the Springfield telescope, where there's a pier that goes up, you climb up a ladder, you sit in a little cockpit type chair, and that's adjustable. You have to get off of it to adjust it. And then you have this huge telescope. It's at least 10 feet long with a huge counterweight on the top, must weigh at least a ton. And you sit in there, and regardless of where you move the telescope, you can look in the eyepiece and it stays there. Now, it didn't have, I don't think it had a clock drive, but I think it had a manual drive. You can adjust it. For the time, it was amazing. So he was really ahead of his time. So to have a picture of something that he did, I really, really appreciate it. It's really nice. Something I'll treasure.
Well, thank you, Mike, for everything you've done. Jeff, we're on time. Okay. They asked me to say some closing remarks as your new president. So I'll start off with a quote from the famous American astronomer Carl Sagan. He said that astronomy is both a humbling and character building experience. And boy, don't we know that as amateurs. We are humbled by everything we learn and see. The technology is moving so fast that we can't even keep up with it. It's just a great time to be an amateur astronomer. So it's also a great time to be part of this Stockton Astronomical Society. Locally here, we've got a lot of great things going on. The activity of our club is just on a rise. We're being asked to do public events and outreach all the time. So I'm humbled, and I think you should be too, by the effect that we can have in our local community through participation in our club. So there's just so many things that there's ways to get involved, ways to join. Just go out Grove Park once a month is a great thing Doug will always remind us of when we're going out there. The awe and the wonder that you see in a young person's eyes when they see Saturn or the moon through the eyepiece for the first time is just irreplaceable. There's no other experience like it. So I encourage you all to stay involved and get involved in any kind of that outreach that you have the opportunity to. And, globally and nationally, we've got just so much going on with our science programs. The rise of STEM locally and nationally, I think is an encouragement that we picked a great hobby to be an amateur in. So with that, I just want to thank you all for coming tonight. Look forward to a great year ahead and good program every month. So thank you all. And with that, again, missing the gavel, but I'll adjourn the meeting by asking for a motion to adjourn. I'll second. Okay, so moved, adjourned. Thank you for all coming.
Let's make an announcement. We can't leave it, it's gotta go, there's plates, 2 salads, some cans of goose, and some. They all have to go home with us, can't leave them here. Thank you.